Okay, welcome to this mathematics tutorial number 1, part of the SE 4030 Key Skills for Chemists module. So I'm going to go through some of the ideas behind the display of numbers today, and the display of numbers is really important for us as chemists because we're constantly working with data, constantly working with numbers, so we need to understand how we can manipulate them and show them in a way that best represents the data which we are analysing or presenting. So in terms of the learning objectives from this tutorial, by the end of this session you will be able to identify the components of a simple algebraic phrase, write algebraic phrases using a standard factor, write algebraic phrases using scientific notation, determine the correct number of significant figures to use, and also the correct number of significant figures to use when performing a calculation, and define the difference between decimal places and significant figures. Now, as with all of these tutorials, I will go through a couple of worked examples. There will then be a number of self-tests for you to complete. The idea is that when we reach a self-test page, you pause the video, you make your way through the self-tests. Once you've completed all of the self-tests, you hit play again and the answers will be shown on the next screen. And again, as with all of these tutorials, if at any point you become stuck, then please do come and find me in my office, or call me on Microsoft Teams, or email me. Okay, so I'd like to start by introducing algebraic phrases. Well, any algebraic phrase will include a number of common things. The first one is a variable, the second is a number, and usually in chemistry, some units. Right? We pretty much always have units in chemistry, unless we're talking about something which is highly theoretical. One or more of the terms in that algebraic phrase may also be multiplied by a factor, and hopefully you'll see that in the worked example below here. So I have a simple algebraic phrase at the bottom of the screen there, energy equals 12 kilojoules per mole. Well, energy is my variable. That's the thing that changes. 12 is the number in this algebraic phrase. Joules per mole is the unit of that number, and finally there's a factor which my units are multiplied by here, k or kilo, telling me that my unit joules per mole is multiplied by 1000 to give kilojoules per mole. So that's the makeup of a basic algebraic phrase. So what I'd like to do here is pause for self-test 1. So in each of the following algebraic phrases, I would like you to identify the variable, the number, the unit, and where appropriate, the factor. Now it may seem basic, but have a go, work your way through them. The answers will be on the following screen when you're ready. So here are the answers to self-test 1. Pause the video, see how you did. Now, we can also write an algebraic phrase with a standard factor, and I want to talk a little bit about these factors, and I'll use an example of the length of a carbon-carbon bond. So a carbon-carbon bond has a length of around 0.00000000013 meters. Very, very small number. Now, for anyone writing that down on a piece of paper, or indeed trying to interpret that number, it's written in quite a ridiculous way because we're not able to comprehend it logically. It has way too many zeros. So it's far easier then to abbreviate that number by writing it as the length of a carbon-carbon bond is equal to 130 picometers, where that p, that factor in front of the unit meter, means pico, where 1 picometre is equal to 0.0000000000001 metre. And we call that term, that pico, a standard factor. And there are a very large number of standard factors that you can use in mathematics. And I've listed there in the table on the left some of the common standard factors that we use in chemistry. Now it's maybe not worth memorising all of these, but it's definitely worth getting to know them. Because throughout your career in chemistry, throughout this course, you will come across the factors in this table and you will need to be able to interpret them and use them appropriately. Note then just on some basic mathematical notation rules, we never print these in italic type, and you'll notice that some of the letters there are capitals and others are lowercase. Okay? Generally, only factors greater than 1 appear in uppercase. So the mega, the giga, the tera, and the peta. So let's have a look at a worked example where we use these standard factors. So burning 1 mole of N-octane liberates 5,471,000 joules of energy. And the worked example asks us to write this energy in terms of a standard factor. And there is N-octane. So in words, we know that the energy released is about 5 million joules. The standard factor then, meaning million, is mega. So we know that's the standard factor we want to use. Now we could easily write this as 5.471 times 1 million joules. But by substituting in that factor mega for million, we gain a far more efficient way of writing that number. And we can write the energy released as 5.471 megajoules. Okay, so pause for self-test 2 now. What I'd like you to do in this test is to rewrite the following using those standard factors. You may wish to refer back to the table where I listed all of the standard factors if you like. Have a go at these, pause the video, and the answers will appear on the next screen. Okay, well, we can also write algebraic phrases using scientific notation. We don't always have to use standard factors. And scientific notation is a different form of shorthand to the standard factors that we've seen on the previous slides, but it fulfills exactly the same function. So, the speed of light in a vacuum, c, is 300 million meters per second. Now, again, it's a really large number, it's a cumbersome number, we want a much more efficient way of writing it. So many people, many scientists would much prefer to write that large number using scientific notation. And how we do that is we split the number into a 2 or 3 digit number, generally with a decimal point, followed by a factor. So in this case, 300 million becomes 3.0 times 10 to the 8 meters per second. And what we do then, using this form of notation, is that we avoid the use of those standard factors that we saw in the table a few slides ago, and we simply write the factor as 10 raised to an appropriate power. So let's have a look at this worked example. The worked example requires us to write the Boltzmann constant, Kb, in scientific notation. And I give you there the value of the Boltzmann constant in joules per Kelvin. You can see that it's a very, very small number and has lots of zeros after the decimal place before we get to that final 138. So our aim when using scientific notation is to write a number that has the form of a dot b times 10 to the c. So we know that that number a dot b before our factor 10 to the c will be 1.38. We can see that by looking towards the end of the Boltzmann constant written there. We know that the decimal point is 23 places to the left of the 1, which is another way of saying 10 raised to the power of minus 23. And we very simply multiply the answers that we gain from 1 and 2 to obtain 1.38 times 10 to the minus 23. And finally we include units, so we write the Boltzmann constant there using scientific notation as 1.38 times 10 to the minus 23 joules per Kelvin. Right, so pause for self-test 3 now. There are two examples of numbers there, the Faraday constant and the formal charge Q on an electron, a very small number. I'd like you to rewrite those in scientific notation, and the answers, pause the video, the answers will come up on the next slide. So the next thing that I would like to go over in terms of the display of numbers is the use of significant figures. And we're going to take a trip to the museum as an example here. So let's imagine we take a trip to the museum and we see an exhibit which shows the fossil of a great dinosaur. And there's a plaque next to that fossil which tells us that the fossil is 100 million years old. Now let's imagine that we return to that exact same museum to have a look at that same fossil exactly 1 year later, but now there is a plaque next to the fossil which says that it is 100,000,001 years old. Now, upon returning to the museum, that extra 1 tells us absolutely nothing when we compare it to the huge number of 100 million. And indeed, it is actually impossible for us to tell the age of something that precisely. So we can't cite it that precisely. We wouldn't ever say that's 100,000,001 years old. We'd simply say it's around about 100 million years old. And the number of significant figures that we use in chemistry makes a very powerful statement about the precision of the method or experiment that we're using. And this is a really, really important point in chemistry, because we are limited by the method and the instrumentation that we are using. If I measure the concentration of an element within a sample, then I'm limited by the precision of my equipment or the method that I'm using. I can't suddenly report that to 10 significant figures because the instrumentation I'm using isn't capable of measuring something to that degree of accuracy. Let's have a think about that a little further in terms of the measurement of an enthalpy change. So I show you there in the blue box a measured enthalpy change, delta H, of 12 kilojoules per mole. By presenting the numbers in that manner, I'm saying that the technique and the instrumentation that I used to measure the enthalpy change was incapable of distinguishing between enthalpy changes of 11.5 and 12.5 kilojoules per mole. So the number of significant figures that I use to report my data tells the reader, makes a statement on the accuracy of my experiment. However, if I have a far more accurate way of determining the enthalpy change of a reaction, for example, and I then report my enthalpy change as 12.58 kilojoules per mole, I'm now implying that the actual value lies somewhere between 12.575 and 12.585 kilojoules per mole. So by presenting my data in that manner, I'm saying that my experiment is 100 times more precise than the experiment I used in the blue box. So you see, by careful consideration of data presentation, by thinking about the number of significant figures that I present my data to, or the results of my experiment to, I tell or say something about the accuracy of the technique that I was using. This is a really, really important point when you guys come to write laboratory reports, for example, and analyse data. Okay, so self-test number 4 now. Pause the video, have a go at these self-tests. I would like you to re-express each of the following with a smaller number of significant figures, and the required number of significant figures is given in square brackets after each algebraic phrase. Have a go, pause the video, answers will be on the next slide. Now, I just want to have a quick run through of actually using significant figures, and particularly using significant figures when performing some kind of calculation, in this case a multiplication or a division. Now, actually what you'll find as you start to play around with data and as you start to perform experiments in the laboratory, you will often have to perform calculations, in this case multiplications and divisions, with numbers that are expressed themselves with a differing number of significant figures. Now, we've just spoken about the importance of presenting and choosing the correct number of significant figures. So what do you do if you have to perform a calculation on two numbers that are displayed with different significant figures themselves? Well, we have to express the final answer of that calculation and round that answer off to as many significant figures as the value with the least number of significant figures. So there is a kind of limiting precision here, and it will always be the value with the least number of significant figures. So let's have a look at a worked example here. Let's imagine that we are studying a kinetics experiment, and we wish to study the rate of formation of this sweet-smelling ester, methyl salicylate, from the combination of methanol and salicylic acid. You can see the reaction scheme in the white box there. We can express the rate of this reaction as K, the rate constant, multiplied by the concentration of methanol, multiplied by the concentration of salicylic acid. And you may remember these kinds of equations from your studies at A-level or college. Now, I give you here values for each one of those parameters in that algebraic phrase. The value of the rate constant K is given as 3.06 times 10 to the minus 4 moles per decimeter cubed. The concentration of methanol is given as 5 moles per decimeter cubed, and the concentration of salicylic acid is given as 0.45 moles per decimeter cubed. What you'll note then is that all three of those numbers are expressed in terms of a different number of significant figures. So the first thing we do is forget about that and calculate the rate anyway. So the rate is equal to 6.885 times 10 to the minus 4 moles per decimeter cubed per second. Then we have to look for that variable with limiting precision, and when we look through those numbers we see that it was methanol, the concentration of methanol, because it was only expressed to one significant figure. What's important about that then is that we can only express the answer itself to one significant figure. So although when we calculate the rate using those numbers we get a value of 6.885 times 10 to the minus 4 moles per decimeter cubed per second, because we have a variable or a value within that algebraic expression that is only written to one significant figure, we must therefore write the answer of our calculation to one significant figure. So the correct answer here is that the rate is equal to 7 times 10 to the minus 4 mole per decimeter cubed per second. Okay, so pause for self-test 5 here. I would like you to calculate the following multiplication and division problems, and I would like you to cite each answer to the correct number of significant figures. so you'll have to look for the variable with limiting precision in each case. Pause the video, answers will be on the next slide. The last thing that I would like to consider is the use of decimal places. So this tends to be important when we add or subtract numbers. And when we add or subtract numbers, we tend not to use significant figures. Instead, we use decimal places. So let's go through a quick worked example. A current is measured and comprises the following three components. I analyte equals 5.37 milliamps. I double layer charging equals 43 microamps. And I side reactions equals 1 milliamp. The question is, what is the total current expressed to an appropriate number of decimal places? Well, we can calculate the total current, and that's obtained by adding those three components. And the final example we get, the final value we get is 6.413 milliamps. But you'll note here that the I side reactions component is only written to 0 decimal places. So we have to use that as our variable of limiting precision, and we can therefore only write the final total current to 0 decimal places. So the correct value here is 6 milliamps. Okay, so pause for self-test 6. This is very similar to self-test 5, but using decimal places and addition and subtraction problems. I'd like you to perform the addition and subtraction problems and cite each answer to the correct number of decimal places. Have a go at them. Answers will be on the next slide. Right, well that's all we've got time for today. Thank you very much for listening. Thanks for having a go at those problems. If you would like to discuss any of the contents of this tutorial, then please send me an email to arrange a time. And I look forward to seeing you in the next tutorial. Thanks very much.